great pleasure, needless to say, to be here. And I'd like to express my thanks to the university and to Gene Hawk and to all his worthy helpers that have been so kind already to us, showing us around town and delivering us to wonderful restaurants. And I look forward to more of the same. Now, in figureality, I think this conference comes at a very appropriate time, because if we think back, trace back the history of this concept, it goes back at least in recorded time to the Greeks and perhaps further, comparing Democritus versus some of the other, Heraclitus and some of the other Greek philosophers who emphasized more the way that things must come together. So it goes way, way back, and we see it over the centuries surfacing again and again in the philosophies, for example, in the 17th, 18th, and 19th centuries, with the birth of Berkeley and Hume and the British empiricism versus the phenomenologists. And later on, actually, as scientific psychology began to develop, we have the behaviorists who are more analytic, emphasizing things that we think of as more independent kinds of components versus the Gestalt psychologists. But we really haven't had a science that was a science, say, of psychophysics in a very hard-nosed sense, in the same spirit, for example, as Wundt and Fechner and Helmholtz and people like that in the 19th century, who began to study sensory processes and perception in a very scientific way for the first time. Unfortunately, while everybody has understood, well, almost everybody has understood that ultimately almost all, and maybe it's an overstatement, but a huge amount of human psychology, perception, and cognition is intertwined and very difficult to extricate into individual independent components. But we have not had the theory and methodology that allows us. Is this a better one? That sounds like it's already going to be better. Now I'm going to sing you a little song from Frank Sinatra. Just kidding. You would not want that. So, even with the advent of signal detection theory in the 1940s and 50s, and psychologists, by the way, as some of you know, were really influential in that, working alongside applied physicists and engineers at the University of Michigan, which are vice president there, has his degrees. But unfortunately, when you went into the multivariate situation where you had more than one dimension to contend with, even the signal detection kind of theory that was being used by the engineers and physicists could not be really employed very well by psychologists because it was very complicated. We didn't have the computing power to estimate parameters in such a complicated model and so forth. So my students and I, especially Greg Ashby, in the 70s and 80s, began to develop ways of using multidimensional signal detection theory in such a way as to test independence of various psychological dimensions. And we were able to skirt or to avoid the pitfalls of complexity in this complicated theory by developing, we could call them quantitative ideas, i.e., that is, ways of testing the concepts in a non-parametric and distribution-free way. So it was not necessary, at least at the first stages, to have very powerful computers, which didn't exist really in the 80s, although they were beginning to develop, to test these in powerful ways that did not depend on specific parameters and specific model structures. So we'll look at the a little more history of the way the theory and the applied methodology evolved. Now, in my lab, we like to call it a kind of meta-theory because the idea is to develop a very broad theory that covers many, many kinds of models and to make the first decisions as to the model classes through powerful experiments and powerful methodology that does not depend on a specific model. Okay. And we call that the sieve approach, SIEVE, which means a kind of filtering or winnowing down, because we feel like if we first make the division of major models, like we've studied parallel and serial processing, and some of the other speakers will emphasize for many years, then when you say you know that it's some kind of parallel processing, then that allows the investigator to begin with more computational and specific kinds of models to get ever more precise kind of characterization of human behavior and the underlying cognitive systems. So again, I won't be able to spend much time with the history, but this is kind of modern, more modern history, starting with the 19th century. And we jump into the 20th century with Thurston, who was kind of a psychometrician, type of psychologist, but was also maybe unwittingly beginning to do some of the first mathematical models, because he not only did test theory along traditional psychometric lines, but he also began to work with all this theory. I'm ready to read code, so I often can't see these at all. I can barely see this one a little bit, but I think it's fine. The discriminal, of course, this was really a psychological model about how people made psychological discriminations based on underlying normal, so-called normal or Gaussian distributions. And oh, by the way, please feel free. This is, my understanding is that the entire conference can be considered as a workshop, so I invite questions at any point in time. And then later, this was kind of a grandfather of the later signal detection theory, as I mentioned, really getting started in the 40s and 50s. A lot of it because of work that was going on for military purposes in the Second World War. And a lot of it in Michigan, and there were some psychologists you may recognize, and also some physicists. So we have kind of Sweats, Tanner, Green were all psychologists, but these other guys, Birdsall Fox, Ethan was actually also a psychologist. Birdsall Fox were tied in the war electrical engineers. So I won't go through the detail, but just quickly remind you, because this is kind of what Thurston was doing, was really employing what we now call statistical decision making or hypothesis testing, but using it as a model of human behavior. And I wish I could stop and go through every notation, but we won't have time for that, unfortunately. You see the two distributions, and in this case, you're supposed to tell which thing it is, and you have, it's not only good for yes-no experiments that came along later with signal detection theory, but any kind of discrimination. And Thurston had the various, you may recall, had the various versions, the simplest of which assumed no correlation and equal variances and so forth. And this was a decision strategy, so that probability of choosing object x2 is a probability that x2 is greater than x1, and it's easy using normal distribution theory to make those computations. And signal detection theory became more sophisticated. Much of it is still basic statistics. There is also the ideal observer theory, which relates the statistics to underlying physical notions such as signal-to-noise ratio. So it's really quite beautiful theory. But most of the way it's used in psychology and cognitive science is still at the statistical level, in particular statistics of importance of things like the likelihood ratio, probability of hits and false alarms and so forth. So starting back around then, there was explosive development and connections with things like information theory from Claude Shannon and stochastic process, prediction theory, filtering from Robert Wiener and others, as well as cybernetics. Psychology began to use back in the 60s, or early to mid-60s, began to use signal detection theory and memory, for example, as well as psychophysics. But it never went much beyond that in terms of considerations of more complex kinds of signals. So again, this is just repeating what I said early on in the first part of the lecture, that while it was straightforward for engineers to build machines that acted like this, it was extremely challenging for psychologists to use it as a black box model and go back in and test the theory with regard to potential theories of the underlying perceptual functions. So Tanner had a paper that's worth reading for historical purposes alone. It was began to try to make inroads into this problem of multidimensional situations, and in his case I believe it was loudness and pitch were the two dimensions, if I'm not mistaken. But it was very, very limited, made some assumptions that were simply too strong to last very long. So around this time, my group became interested in feature models of pattern recognition, which were all the rage back in the 70s because of the influence of the psychophysiology of people like Hubel and Wiesel, who found the feature detectors in early to later visual stages of the cortex. And these models were also picked up very fast by computer scientists such as Selfridge and others, with this famous Pandemonium model you may have heard about. And psychologists began to develop mathematical models, people like David Reinhardt, that could be tested in the laboratory. So they were given explicit mathematical form, or what we call analytic form, and then these made predictions which could be tested in the laboratory. However, it seemed to me that at the time that the tests, while interesting, using things like the alphabet, which I also did, using the uppercase English alphabet in some studies in 1971, that these were not testing the fundamental aspects of the models. These models were based upon very, very strong assumptions about how the features of letters or faces or whatever were processed and should be tested in a more direct way, and that led us down this field of research. I might mention also that in terms of configurality, that in my mind it's very difficult, if not impossible, to rigorously define what configurality is if you don't know what the lack of configurality is. So that led us to our study of independence, and it turned out that psychologists by and large were confusing a number of different kinds of notions of independence that really are very separate. In terms of, if you build a system, you would have to consider these different notions independent of one another, depending on the system you wish to build. So, so we're going down that line. And here's one of the first kinds of independence. This was assumed in all of the substantive or computational feature models at the time. And this was one of the assumptions that was usually stated explicitly. In some cases, we'll see some notions or assumptions that were not really made explicit. But this one, sampling independence, it was sometimes called extraction independence. But to our group, this had too many connotations of physiology. And there was no really direct connection of these models with the physiology. So we chose the more neutral term, sampling independence. And sampling independence also is an observable, and we'll see it throughout this lecture. It's one of the ways that you actually see it in behavior. And we see it basically, this one is at the report level, because it's observable, we later will pick up the term report independence, but they're the same thing. So basically, it's according to the usual statistical definitions, the probability of reporting, say if you present a certain stimulus like the horizontal and the vertical line there, that the probability that you get both of those features correct would be the product, or the product of the two marginal probabilities. And that, of course, is statistical or probability.